Hello, in this video we are going to be looking at indefinite integrals. So the goal here is to define something that's going to be the opposite of a derivative. If you know the derivative of a function, then finding the function itself would be called anti-differentiation. So then you would use this process to find an antiderivative. You can imagine that if you have a function and you take its derivative, so take the derivative, it gives you the first derivative. If you take the derivative again, gives you the second derivative. Is there a way to go back up this chain? Could I get from here, back up to here, back up to here? The answer is yes. We call it anti-differentiation. So this process of going back up the chain is also called integration. And if you have used integration to find a function, then the thing you have found is the indefinite integral. Usually we just call this the integral. Let's look at a function where we take an antiderivative. So let's suppose that f prime of x is equal to 8x cubed plus 3. Now, I would like us to find f of x. What we are being asked to do here is to find an antiderivative. You have a derivative function. You need to find the originating function. What was the original function that gave us this as its derivative? So what is the antiderivative of 8x cubed plus 3? Well, initially, we will eventually develop like hard and fast rules that we can use, but initially we just kind of do this by inspection. We think about it, we try something, and we might have to adjust our process along the way. Now, I look at the original function. I'm going to start just one piece at a time. So 8x cubed, I need to think of something whose derivative would be 8x cubed. Now, you may just immediately know what the function is. That won't always be the case. But I'm going to start with x because I see that there's an x up here. Then I would ask myself, what exponent should I use here? So when I compare this exponent and this exponent, what I know about differentiation is that if I had an exponent, whatever my exponent is here, when I take its derivative, I would have to decrease by 1. So let's guess what would happen if I put a 3 here. Well, the problem is then if I take this derivative, I would get 3x squared, and because it's reduced down to 2, it doesn't match the thing that I want. So 3 was not a good guess. All right, so let's go back. Let's erase that. Let's get rid of this. I'm going to go and pick 4. 4 seems logical. So now if I take this derivative, I would get 4x cubed. Well, that's not everything I want, but it's the exponent that I want. So I'm very happy with the exponent. Now I'm going to go look at the coefficient, and I'm going to ask myself, what coefficient would I need? Because right now when I take this derivative, I'm getting 4, I'm not getting 8. So then we could decide, oh, maybe I want to have a 2 in here. So if I put 2 in here, let me go ahead and erase this derivative that I'm taking here. Then 4 times 2 would give me 8. So this looks great so far. I have the first piece in check, in tow. And I need to decide what should the rest of my function be, because I don't have 3 yet. So I need to think of what would I have to have here. Is there a function whose derivative is just 3? And then we recall, and we're like, oh yes, if I added on 3x, the derivative of 3x is just 3. So this accounts for all of our given information. What I have is a function that gives me this derivative, but you may think to yourself, this is not the only function that has this thing as its derivative. Yes, we found one example that has the right derivative, but what if, let me add this in red, what if I added on plus 2? Well, if I add on plus 2, then when you take this derivative, taking the derivative of a constant gives you 0. So yes, this function would also have the correct derivative. Well, what if I change the plus 2 to something else? What if I changed it to be minus 7? Then you look at this and you're like, yes, you have still done the thing. This is a function whose derivative is this thing up here. So we have a little bit of ambiguity when we take an antiderivative. This number at the end, this constant, could literally be anything. So at first glance, it's like, oh man, there are an infinite number of antiderivatives of this function. The way we're going to account for this is instead of picking a number like 2 or 7, what I'm going to do is I'm going to just add in an arbitrary constant, and what we use for this is we use the capital letter C. So there might be situations, like if you were in the context of a word problem, where you would want to specify what C is, but the generic antiderivative is always going to have this plus C. So we end up calling this, because we normally call this integration, so we're going to call this plus C the constant of integration. All right, all of this work that I've done has been in the thought process of thinking about derivatives. So I've been using derivative notation. When we talk about integration, we do the exact same thing that I just did, finding an antiderivative, but we're going to frame it differently with different types of notation. So I could ask you to find, okay, I'm going to ask the exact same question just using different vocabulary. Find the indefinite integral of the function f equals 8x cubed plus 3. So one difference in my notation already is that I'm not specifying this is a derivative, but the implication is if you're finding an indefinite integral, you need a function whose derivative, when you take its derivative, you get this. So if this is not being specified as the derivative, what I'm going to do when I compute my indefinite integral is I'm just going to call it capital F. And the implication here, when you look at these two, and you'll see this just kind of all throughout integral calculus, when you have a lowercase function and a capital letter function, the capital letter is the integral of the lowercase letter. Now, that's just kind of a convention that we use. It's not like a strict definition, but it's something that you're going to want to start getting used to seeing. Okay, so then what would this be equal to? Now, let me remind you, let's go back here to this derivative notation. I called this f prime when I was taking the derivative. Another way for me to take a derivative, let's see if I can squeeze it in here. I could have said d dx, so the derivative with respect to x of 2x to the fourth plus 3x plus c is equal to this function. So this d dx tells me I'm taking a derivative, then the brackets just tell me what I'm taking the derivative of. We're going to have something similar like that for integration. The symbol is a new symbol if you've never seen it before. It's called an integral sign. It just looks like almost like a really stretched out S, and it means I need to compute the indefinite integral, or the antiderivative of the thing that's inside. Now, at the end of this, we do need to specify some notation here, and it needs to specify what was the variable that we were working with, because eventually, we might start thinking about different kinds of variables. So what we're going to do is we're going to specify we are doing this with respect to x. So we want a indefinite integral with respect to x. All this is saying is whatever I put in here, you need to find the antiderivative of. So the way we would convert this notation is we would say, all right, I'm finding an antiderivative of 8x cubed plus 3. So then I would say, all right, if f was equal to that, then what would that be? Well, based on our previous work, I know that if I have 2x to the fourth, the derivative of that gives me the 8x cubed. If I have 3x, then the derivative of that gives me the 3. But I know that I always have to have a I might have any constant at the end, so I'm just going to add a capital C, which is my constant of integration. So this notation here and this notation here mean exactly the same thing. All right, having seen our first example, let's talk about the generic process for finding antiderivatives of powers of x. So what this says, if you ever wanted to compute an antiderivative of x to the n with respect to x, or another way of saying that, if you wanted to compute an indefinite integral of x to the n with respect to x, what process would we have to use? Well, we have already seen it happen one time. We had x to the 3, and when we wanted to compute its antiderivative, we realized we were going to have x to the 4. So the exponent had to increment by 1. And that's what this rule says here, is you're going to take x, but instead of using the old exponent, you're going to increase it by 1, so that when you take the derivative, you can decrease it back to the original thing. And then when you do this, you will also have to divide by n plus 1. You might ask yourself, what do you mean? I don't feel like I did that. Well, it did happen. So if you look at the 8, like how did 8 become 2? One way to think about that is you took the 8 and then you divided it by 1 more than what the previous exponent was. So 8 divided by 4 was how we got the 2. And then when you think about it in the forward manner, or in the derivative manner, I should say, 4 times 2 gave us 8. But if you're thinking about an antiderivative, 8 divided by 4 gives us 2. So that's all the rule says. And then, well, okay, it also says you have to add on plus c at the end. We only ever do this when n is not equal to -1, and we can talk about that in a later video. Okay, let's go ahead and look at a couple more examples where we use this property. So I'm going to start using this integral notation. Let's find the indefinite integral of x cubed with respect to x. So I've said it before, I'm going to say it again. This indefinite integral and this with respect to x, the dx, we would call it a differential. These two symbols are basically just a notation that says find the antiderivative of x cubed. You have to have this or we don't know what we are doing. Like, if you don't have the integral symbol and you don't have this, then it doesn't mean anything. It's just like, hey, I have a function. But when you have the integral symbol and the differential here, then it's telling us, yes, you have to find the antiderivative of this thing. Okay, well, let's apply this. So this would be equal to, we have x, we're going to increase the exponent by 1, and then you have to divide by something. Well, you divide by whatever the new exponent is, like this, and then at the very end, you add on plus c. So plus c. Now, this is the answer. How do I know if this is correct? You could take the derivative of that. So what is the derivative of x to the 4 over 4 plus c? Well, it would be the 4 in the exponent comes out in front, but then it reduces with the 4 you're dividing by. So 4x cubed divided by 4 just becomes x cubed. What is the derivative of your constant? Derivative of any constant is just 0. So we end up getting x cubed. And the fact that we have the same thing that you started with is how you can check your work. You know that you are correct because we took a derivative and we got the correct answer, which was stated here at the beginning. Let's do another example. We have seen functions where we had negative exponents. So let's go ahead and say, let's find the antiderivative of x to the negative, I'll pick -2. Well, how do we think about this? We think to ourselves, I need to start with an x. I'm going to increase the exponent by 1. So think to yourself, plus 1. -2 plus 1 would be -1. And then you would divide by whatever the new exponent is. So x to the -1. Oh, I'm sorry, I almost forgot my plus c. Let's add in the plus c. X to the -1 divided by -1 would be negative x to the -1 plus c. This is correct. If you like, you could write this as -1 over x. That's also correct, plus c. And For either of these, if you take the derivative, I'm not going to actually go through this process of checking it every time, but if you take the derivative of this function, you will find you get x to the negative 2. Well, let's look at another example. This time, let's find the indefinite integral of x to the negative 1/2 with respect to x. And you do the same process that we've been doing. So we start by just writing down the x, then we think about what should the new exponent be. It's got to be one more than the previous one, so I just take this number plus 1. Now I'm going to do this in my head. I'm going to get 1/2. But what you're thinking to yourself is you're thinking negative 1/2 plus 1 is how we're getting that number. Then whatever the new exponent is, you divide by it. So we divide by 1/2. And you have to add on this plus c. Now this is pretty ugly, but I'm going to change the, I'm going to simplify my denominator. So if you're dividing by a fraction, this would be the same thing as multiplying by the reciprocal. Let's go ahead and write this here. So this would be the same as 2 over 1 times x to the 1/2. Right? We just changed division of a fraction to multiplication by the reciprocal. Let me not forget this plus c. So my final answer here is 2x to the 1/2 plus c. Now, that may have felt really like awkward and a little bit clumsy going from here to here to here to here, but now that you're looking at this function at the end, hopefully you would say, like, oh yeah, I know how to find this derivative. The derivative of 2x to the 1/2 plus c, you would take 1/2 times 2 to get 1. Then you would decrease the size of the exponent by 1. So if you take 1/2 minus 1, you get negative 1/2. The derivative of a constant is 0. So yes, the derivative of this thing does in fact give you what you started with. What we would like to do next is we would like to expand our understanding of these indefinite integrals. So every time there is a derivative rule, there will be a corresponding integral. If you know that the derivative of x is 1, that means the antiderivative of 1 is x plus a constant. There was a rule that said if you have a coefficient in a problem, or just some constant being multiplied to your function, then when you take its derivative, it's allowed to hang out in front. Well, there's a corresponding property that says if you're taking an antiderivative and you have a constant just hanging out in front, well, you can wait till the end and just have it hang out in front the other way as well. So this coefficient will just stay there, and then you can think about the antiderivative of the rest of the function. We had a derivative rule that said you're allowed to add and subtract separate functions, and you just take the derivatives separately. So then the corresponding integral rule would be if you need an antiderivative of two separate functions, you can just think about them separately. So that's all these rules say. Let's go ahead and apply that in a couple of examples. So indefinite integral of 4 with respect to x. One thing you should keep in mind on any of these problems, what I'm asking you to do is come up with a function whose derivative is the inside part. And sometimes when you remind yourself of that, it just makes the answer like kind of obvious. In this case, the answer would be 4x because that's the function whose derivative is 4. And then I'm going to add on plus c because we always have to add on a plus c when we're doing antiderivatives or these indefinite integrals. Let's do another function. So how about 8x to the 5th with respect to x? Well, I'm doing an antiderivative of this function here. So I have a coefficient, the 8, it's just going to hang out in front. Then you can write x to the, and you're going to have to come up with some new exponent here. We had a rule on the previous page that says I just get to add 1 to the exponent. So let's increase that to 6. And then we immediately divide by whatever that new exponent is. So if you're ever like forgetting, like, do I divide by the new exponent or do I divide by the old exponent? Just ask yourself, could you take the derivative of the thing you just wrote and get back to the previous line? So if I take this derivative, 6 comes out, reduces with the 6, gets me right back here. And if that had been a 5, it would not have worked out. So what this is I'm trying to illustrate here is that The 8 was the coefficient. It just hung out until the end. We took the derivative of the rest of the function. Now we'll simplify this together. I should not forget my plus c before I start simplifying. So 8 divided by 6 would be 4/3 x to the 6. That's plus c. What about the indefinite integral of x cubed plus 4x with respect to x? So you need to find some function whose derivative gives you the thing that's inside parentheses. We'll do this one step at a time. So I think about x to the third, and I increase the 3 to a 4 and divide by 4. Then we add on. There's a constant, not a constant, like a coefficient on the x. It's the number 4, and then I write x. I'm going to increase its exponent by 1. So the previous exponent was implied to be 1, now the new exponent is 2, and then you just divide immediately by whatever the new exponent was. We add on a plus c. This is our answer, but we do want to simplify it. It doesn't simplify a ton, x to the 4 over 4 plus 2x squared plus c, but it's nice to have seen that at least this 4 divided by 2 did simplify. All right, we have a couple more examples. What about something like x squared minus 4 squared with respect to x? So what you're going to see here is you have a function being raised up to an exponent. So this is like a function inside of another function. Now, if you think about derivatives, you have to have a special chain rule to take a derivative of something like this. When we have integrals, you also have to have special rules. So we are not ready, we don't have the rule yet to think about what this derivative would be. So we're going to have to take an alternate strategy to computing this. But you're not allowed to just increase the 2 to a 3 and then divide by 3, or this 2 to a 3 and then divide by 3. Like, those processes just don't work when you have a function inside of another function. So what could we do instead? I know that x squared minus 4 squared really means x squared minus 4 times x squared minus 4. So I'm going to just FOIL that out. What I would get is I would get the indefinite integral of x to the 4 minus 8x plus 16. This is with respect to x. And now this is just a single function, and I can take its antiderivative no problem. So the antiderivative here is going to be x to the 5th over 5 minus 8x squared over 2, then plus 16x. If you're following this pattern and be like, why didn't we divide anything? It's technically x to the 1 over 1, but we never show that because, right, it's just 16x is the function whose derivative is 16. Don't forget your plus c. Also, don't forget to simplify. So x to the 5 over 5 minus 4x squared plus 16x plus c. Let's look at an example where we have some kind of a root. So what is the antiderivative of 3 times the 4th root of x with respect to x? Well, before you start, you want to rewrite the root so that it's x raised up to some number, in this case x to the 1/4. And once it is raised up to some number, then we can just proceed. So this would be 3 x to the new exponent is going to be 1 larger than the previous one, so that'll be 5/4. Then you immediately divide by 5/4, add on your c. When you divide by a fraction, that we can simplify this by multiplying by its reciprocal, or just change it into multiplying by the reciprocal. So 3 times 4/5 x to the 5/4 plus c ends up being 12/5 x to the 5/4 plus c. And that'll be our answer. The last example that I would like to look at is going to involve a little bit of, like, I won't call it an algebra trick, but it's something that initially doesn't look solvable until we realize that we can use algebra to simplify this. So if we try to take this antiderivative, like, can you think of a function whose derivative is this thing? Like, seems kind of difficult. Off the top of my head, I cannot. We remember that, yes, there is a quotient rule for taking derivatives, but like that was its own entire separate rule, and we've not talked about anything like it for antiderivatives yet. So you kind of look at this and you scratch your head a little bit until you realize, hey, in this case, I'm only dividing by a single term, so I can split this up into two separate fractions. And that's what I'm going to do. So this is the antiderivative, or the indefinite integral, of x over x to the 4 plus 4 over x to the 4 with respect to x. All right, give myself a little bit more room here. Okay, so how do we handle this? We do need to simplify x over x to the 4 would just be 1 over x cubed. So this is the antiderivative of 1 over x cubed plus 4 over x to the 4 with respect to x. We still need to simplify, or not simplify, but convert. I would like to see all of these x's in the numerator. I would like them to have negative exponents if they were in the denominator before. So you look at this and you're like, okay, well, that's x to the negative 3 plus 4x to the negative 4 with respect to x. All right, now that you're looking at it in this format, I'm willing to proceed. So the antiderivative would be x to the, I need to pick some new exponent, and be careful when you have negative exponents that you're working with. My new exponent needs to be one larger than this, so I'm going to add 1 to it as I go across. So that would give me negative 2, and then I would divide by the new exponent. Then you add on 4x to the negative 3, because we added 1, divided by negative 3, and plus c. So this here is our answer. There's not much you can do with it. If you are interested in simplifying, one way that you could show this is you could say this is negative 1 over x squared. Then 4 divided by 3 is 4/3. It would be negative, so we'll have minus 4/3. X to the negative 3 would have to go down into your denominator, so then it would look like this. But both of these are fairly equivalent in my mind. All right, that finishes out our very first look at antiderivatives. Hopefully this is helpful, and we will expand on these ideas in future videos.